It's my pleasure to introduce James Phillips. James is the lead Consul engineer on the Consul project. He's been with HashiCorp a very long time and one of the smartest people I know. So please give it up for James as he talks to you about Consul.
I'm here to talk about Consul, and Consul is a little bit different than all of our other tools in some interesting ways. We're not a plane shape, we're actually kind of like a pipe that connects our different tools, and there's reasons for why Consul has the pieces it has, and we'll kind of talk about those. So for example, in Vault, it's the preferred storage engine for your actual secrets. It's used by the different Vault instances to coordinate a failover. Nomad has a first-class integration with Consul, so it's how you can publish, once you place jobs on your big fleet of machines, you need to have your applications find each other. So it's used for that. So slightly different roles in different contexts. And we'll go into some of the details about how sort of Consul came to have the capabilities it does. And it's a little bit of a nerdy tool, kind of. It's sort of hard to explain sometimes. So hopefully we can clear up that. And we're going to take an approach where we go kind of low level and work our way up, and we'll talk about Consul kind of in two different use cases. Massive scale in terms of having a single cluster with a massive number of nodes, and then massive scale in terms of having many, many clusters all federated together and how you manage that. And then we'll sort of wrap it up with an example that ties those two cases together. But we'll start with just kind of an overview of Consul. So what is Consul? It's our service discovery, configuration, and orchestration tool. The sort of bread and butter of what you do with Consul is register services. And a service is really just an IP and a port. And you can also associate health checks with services, and we'll talk about that. You can do it via configuration files. You can do it via API. When you actually want to consume services out of Consul, you can discover them through its DNS interface. It has a HTTP interface, so you can do sort of a first-class integration to pull services out. You can do load balancing without a load balancer, even with a client that just does DNS with the result shuffling. It also has a KV store, so you can manage things that are sort of dynamic in your environment if you want to control feature flags or have additional information associated with a service that you need to consume at runtime, or you might want to change at runtime. It has a full KV store. The KV store has orchestration primitives, so you can coordinate things like locks. You can watch for events, so you can have things that efficiently wait for a key to change and take some action, like enabling a feature or turning a feature off. And there's a ton of ways to integrate it with different applications. So we mentioned DNS, the HTTP interface. There's a tool called Consul Template that'll take information from Consul and put it in a config file and send your process a signal. We have a similar tool for environment variables. So there's a lot of different ways to glue it into whatever you have, from like a fully legacy, some crusty binary you don't even know how to compile anymore, can talk to DNS. Or you might do like a first-class integration and talk to our APIs directly. So the full spectrum of applications can be accommodated in Consul without having to rewrite your stuff. Another important piece of Consul is monitoring at scale. So it's not that useful to publish a bunch of services if you can't tell which ones are working and which ones aren't. And this can be applied at the host level, so you can have sort of host level things like memory and disk space, and you can have service level. So you can say, connect to my thing, make sure TCP connections work, hit this endpoint, make sure you get a response code that's good. You can do a sort of a TTL dead person switch, so you can say, you can register a check and say, my service needs to reach out to you, and if you don't hear from it in 20 seconds, there must be something wrong. So there's a lot of different flexibility in how you do health checks. And then the final sort of component of Consul is it's highly available. So within a cluster, it's fault tolerant. It uses RAF to keep consensus, so you can run multiple redundant servers and it'll orchestrate the failover for you. You can federate your clusters. So if you have multiple Consul clusters, you can link them together and they can make use of each other, and we'll talk about that in detail. There's some interesting, we'll sort of wrap up with a fourth bullet about failover policies. So there's some interesting things if you have a federated set of Consul clusters. In very, very simple ways, you can configure, try locally, and if you can't find it, go look over there. So we'll see some examples of that. And then coordination. So if you have a highly available service like Consul that has a KV store that allows you to do coordination, it's a nice thing to just offload that responsibility to. So Vault does leader election in Vault in HA mode by using Consul's coordination primitives. It's super nice to have a system to lean on, so you don't have to deploy, or solve all these problems yourself in your applications. When people see what Consul combines, like health checks, service discovery, this DNS interface, a lot of people think like, oh, Consul's this kind of, I don't know, what is this thing? It's got all this stuff. Why did you put all this stuff together? So let's talk about a few of the things that Consul combines and why we did that. So why combine service discovery with DNS? This is a pretty easy one. DNS is the 3.5 millimeter jack that would let you connect to pretty much anything, or with a dongle you could connect to a modern phone too. But it's just a crusty interface that everything supports, basically zero-touch integration. You basically have it look up something like db.service.consul. Where's the database? Consul will provide the IP and port information. And we shuffle the results. So if you have more than one instance of something, you'll get a randomized lookup every time you do a DNS query. So your load will spread across all the healthy instances of your service without having to put a load balancer in the middle. So that's, for people sort of coming to Consul, especially on the mailing list, it's always, I want to feed a load balancer. Like, I'm always kind of like, what are you trying to do? Like, maybe you don't need the load balancer. So it's sort of a subtle property of how it works, but it can eliminate, vast, complicated moving pieces in your architecture. So here's an example. We're just registering a service called DB. It's the database. It's on port 8000. We define some Python script that we want to run every 10 seconds to make sure it's healthy. And we're just, in this case, it's showing an API request. You can also configure things like this through a configuration file. So you can have your provisioner drop files on the same machine as the Consul agent, and it'll pick them up. And then to actually consume that using the DNS interface, this is just a dig to db.service.consul. The Consul DNS server gives you back the information. In this case, it's a SRV record. So from the DNS query, we got port 8000, and we see it's on 127.0.0.1. Pretty simple. So why would you integrate health checks and monitoring with service discovery? You really want a fresh state of the world. You don't want a static catalog. If you just threw the catalog information, didn't have any health checks to close the loop, you might be sending your services off querying things that are no longer functioning. So by integrating those two, Consul can manage a view of the world that's as fresh as possible. It knows what's in service, what's not, and it can automatically pull them out of service. So if a health check fails, it'll pull that service out. If you do a DNS query, it's not going to return that instance anymore. It's that simple. So you don't have to wake somebody up and push a new configuration. If it's in Consul and you've got the health checks provisioned correctly, it's just going to work. So that's why we integrated those two things. Here's a weirder one. Why would you integrate monitoring with a KV store? It's basically the same answer. By having coordination primitives like locks, you can do super easy leader elections with basically a single CLI command. You can say Consul lock and run this command. And if you run multiple instances of that in your infrastructure, only one of them is going to get a lock. The other ones are going to just sit and wait for for the lock to get released. By incorporating health check information about the node that's holding the lock, if the node just drops off the network for some reason, Consul knows to expire that lock in a safe manner, and your other instance will pick it up. So it's a really natural thing to combine those two elements together, and it ends up being really useful. So here's all the code required if you have Consul to run a sort of master and standby highly available service of your foo command. You basically run one on one node. That path is basically just the key name, and foo is the process, the program. Consul lock that key name foo, and then you run another one, and it basically blocks. And if you control C the first, that second one will start running immediately. So super simple, super powerful primitives. For running Consul, the sort of shape of Consul is it's a single Go binary. You run the agent on every machine in your cluster. You designate some hopefully odd number of those as servers, usually 3 or 5. Some people run 7. Those have a special sort of consistent view of the state of your cluster. And one thing that is sort of another pattern that you really need to think of is your applications just talk to their local agent. You don't need a load balancer in front of Consul, because then you have like another level of service discovery problem. How do I find the load balancer? So your applications basically just talk to localhost port 8500, or they talk to the DNS server that's hosted by the Consul agent running on their host. And then Consul figures out if this is a request that needs to go to the servers, I will find a server and send it there. If a server drops offline, Consul will say, let's stop talking to this server, let's talk to this one instead. So by talking to your local agent, you basically offload all the service discovery stuff onto Consul. You don't need a middleman in front of Consul. So here's a picture of that. In this case, we have sort of a simple cluster. It's got 6 clients. So these might be, like if you're running Nomad, these might be your Nomad worker machines. If you're running some application, you might have, some pool of web servers or whatever. You might have your database machine. Basically, any machine that's in your infrastructure that you want to do service discovery with, you run the Consul agent in client mode. And then in this case, we show 3 servers. We use Raft, so there's a leader server at any given time. So that's the one with the star. And they hold sort of a consistent set of, where they hold the KV information, they hold sort of a centralized, consistent view of the catalog. When you query for a service, we've shown it here as an RPC, so the client agents will sort of, under the hood, do an RPC up to the servers. Some of the queries have to go to the leader. The servers will forward between each other. So like all that complexity is hidden from you. You just did a DNS lookup, and it did all that stuff under the hood. And then there's this thing called LAN gossip, so we'll talk about that in a minute, what that means. So that's a really sort of high-level overview of Consul. Let's do our first massive topic, which is massive clusters. So Consul is currently in use in various organizations that we cannot name, but on the sort of 10,000 to 100,000 nodes in a single cluster scale. So you can imagine people who might need that type of scale, and maybe it's those people, I don't know. But how do you do monitoring at that scale? Because you're running potentially host level checks, so you're trying to check disk space and CPU or whatever on all that fleet of machines, and then each of the machines can have hundreds of services running on them that all may have checks running against them. We have sort of a built-in, is this agent a live check, and we'll talk about how that works. So how do we scale that? Sort of a typical approach for health checking is to have like a central monitoring service that goes out, and I mean some things actually like go remote in and run commands, some things are calling APIs, but basically to have a single point of success that has to go out and do all the monitoring. So it'll say, is this service healthy, web 1? This thing will reply, yes. This is super simple, but it doesn't scale very well because the monitoring service becomes a difficult thing to manage in this type of architecture. A nice way to solve this would be to do like an edge trigger thing. So just have the thing that's running web 1 just tell me if it fails. So that scales super well, but if the whole machine just drops offline, that's a problem. So everybody hates that. You can tell they're typing, but they're not saying anything anymore. So how do you do this? I mean, you could do heartbeats, things like that, but they're still going to push problems back onto your monitoring service. That's not going to scale. So how Consul solves this is actually a pretty interesting way. So it uses a gossip protocol that's based on SWIM. So there's sort of an academic research basis for this. And it's the basis of our surf library, which is also a standalone product. And it lets us detect failures with a very small amount of network load that's sort of fixed for any given size cluster. And it propagates that information really quickly, and it converges really quickly. So we'll see how that works. So in this picture, you've got, these are different nodes in our cluster. And the way the gossip protocol works is periodically, any node will randomly pick some other node to probe. So it's going to send it a UDP message saying, ping, are you alive? In this case, it doesn't hear back. So maybe there's something wrong with node X. So the next phase of the protocol is it'll ask some peer nodes to probe that on its behalf. So this is designed to, the paper is actually pretty interesting, but this is designed to mitigate, maybe there's some weird connectivity thing between this node. The consequences of declaring your database down are pretty high. So we want this to be reliable, but we don't want it to take forever either. So we're going to go ahead and ask 2 other nodes to probe it, and then we're going to attempt a slower probe ourselves over TCP. So everything so far has been UDP. The TCP probe gives us some chance to get through network congestion. Potentially, it potentially has retries in there. It also happens to find people that just have their environments configured incorrectly and haven't opened up TCP, which is required for other things. So it ended up being sort of a handy self-help tool, I guess you could say. So we added that to the base protocol. And then in this case, they didn't hear from X either, so they sent a NAC back to node A, so I didn't hear it. We added the NAC as well, so if you read sort of the paper, you can diff it against some enhancements we've made under sort of the heading lifeguard, like it kind of goes with swim. But this was actually an interesting tweak to feed back some self-awareness into node A. So what we would see is in environments, like a lot of folks would try and run on really low-end AWS instances that would crater and run out of CPU credits, and then that thing would just drop packets for 12 seconds. And then that node would start to think that all kinds of other nodes were failed, and it would cause kind of a bunch of flapping in your cluster. So this is one mechanism we added where if A asked the other ones to probe and didn't hear the NACs back, then A starts to say, well, maybe it's me. And it actually starts, it runs sort of a similar process, but it does it in a much more conservative fashion. If you actually do get the NACs, your detection time stays the same. So the sort of magic of Lifeguard is if you're broken, you slow your detection way down and sort of back off. But if everything's working right, the time to do the detection, even though we've added these extra checks, is the same. So it's kind of a cool, it's kind of a magical shell game kind of thing, but we made it better without making it slower, which is really cool. And we're going to publish a paper on this shortly too. But this has been a fun sort of area here, but I'm kind of nerding out on this, so I'm going to move on. So at that point, the direct probes failed. It asked peers, that didn't work. The TCP didn't come back. So this node starts a timer and says X is suspect, and it actually gossips that out to the rest of the cluster. So you can see that the arrows represent sort of the fan out of that gossip message as it propagates around. The sort of performance of it is dependent on the size of the cluster, but it converges very quickly because it has sort of an exponential fan out or exponential propagation. And then I put the star on there. So in this sort of example, the star is actually one of the server nodes. And the server that happens to be the leader, what it perceives coming in through the gossip mechanism is what gets written to the catalog. So that's how Consul can sort of marry this kind of a freewheeling gossip, almost AP kind of system into a consistent system like RAF. So when you query the cluster and say, give me a healthy instance of this service, it's based on what the leader has perceived through the gossip mechanism. So it's not just sort of dynamically sparkling across all your nodes. It gets funneled through one point and pushed through RAF to be consistent. So, and then the timers sort of wait for a while. There's some steps in the protocol I'm not showing here where the node can refute and say, no, I'm still here. And then at this point it says X has failed, and that goes through gossip as well. So all that is the basis of a distributed failure detector, basically. And what's cool about this is you can run the health checks completely locally on the Consul agents. They can report just when things change, so they just send edges back to the servers. The servers don't have to scale and run a bazillion checks across your whole fleet. You just send a few events every once in a while, say, hey, this server, this service is down or this service was added. You only send the events. And then if a node completely drops offline through the gossip protocol, the cluster is going to detect that really quickly and take that into account. So it scales super well. It works really well. It's a somewhat complicated mechanism under the hood, but it's not that bad, and it's actually mostly hidden from you as an operator. So that's why I want to sort of highlight there's like an interesting plumbing piece here that a lot of people don't quite understand. The one other sort of interesting thing, though, is that in order for the gossip mechanism to work, the nodes in your cluster have to be a fully connected mesh. So any node needs to be able to probe any other random node in the cluster. That's a common source of sort of confusion for new Consul operators, is not to realize that you do have to mesh them all network-wise. So everybody has to be able to talk to everybody else on port 8301 on TCP and UDP. And in Consul, is the node alive, the sort of gossip step we talked about, it sort of exposes the surf health check. So when the node drops off and the cluster thinks it's gone, then the surf health check fails. This is a plot showing, it's like a simulation of a 10,000 node cluster with 1% of the nodes dead and 1% packet loss doing like max power gossip. So each node would experience about 300 kilobits of overhead just related to gossip. That's sort of like the fixed size worst case for a 10,000 node cluster. And it's hard to see the numbers on the bottom, but it converges in like under 2 seconds. So like that's sort of the time you would expect for a worst case for your leader to perceive it. So that's a pretty good detection time. And in practice, it's usually much faster than that. And this graph is up and to the right, which is good, but it's leveling out. So I don't know about this graph. We'll move on. So to summarize, for our monitoring at scale, by utilizing the Gossip protocol, we have a pretty small amount of network load that's fixed for any given number of nodes in your cluster. You do need the fully connected mesh, so you just need to appreciate that, and that's required for it to work properly. And the one other kind of wrinkle here is because UDP is involved, we don't have a mechanism to secure this with TLS, so there's a Gossip encryption key that's involved here. So there's a little bit of overhead in terms of like installing keys and rotating them. We have APIs and command line commands to manage that, but there is sort of an extra step to secure the Gossip. It's simple, but it's a step. In terms of benefits though, we get massive scale. We get some secondary benefits too. You have a full membership list, sort of known to every node in the cluster, which helps us do sort of the magic with finding a new healthy server. If a server drops offline, or if a new server gets added, all the clients know about it, within 2 seconds. So that's super nice. For joining the cluster, it's also super robust. So you basically, as a new client being added to a cluster, you only need to know about one other member, and you'll get the whole list. So it's super hard to create islands within a cluster that don't know about each other. Like everybody gets the full list really, really quickly. So it's just super robust. Some people even struggle with like trying to unjoin things. So it wants to stay together, and it works really well in practice. And then the final thing, and this was a whole talk that we did previously, but because you're doing random probes to all the members of the cluster on a periodic basis, we, in Consul 06, we actually implemented a network tomography system. So we feed those round trip time measurements into what's essentially like a simple spring physics model. And you end up with 8-dimensional coordinate system with some fudge factors kind of thing. But you basically get a set of coordinates that let you perform a calculation and get an estimated round trip time between any nodes that you're interested in. So this, we'll show an example of this. We won't dig into how it works. But you end up having basically automatic sort of nearest neighbor routing, which is super handy. So the second category of massive is massive numbers of clusters. I mean, and massive here is like hundreds. I mean, you probably don't have thousands of clusters, maybe, I don't know, but hundreds is where things get interesting. So how does this work? So Consul supports federation. It's supported actually for a long time. So it's multi-data center aware. Every cluster, and in Consul sort of terminology for configs and stuff, it's called a data center. So each cluster has a name. A cluster basically implies you have some set of servers there, and then you have some whatever number of clients as part of that cluster, and then you've done some process to join the servers together so that you can query information from one cluster in one cluster from another, or you can update information across clusters. When you federate, all the communication happens between servers. There's no direct links between the actual clients running in one cluster and the clients in another, but a client just speaking to its local Consul agent can query for some KV store or some service that's in a different data center. And what happens is we'll route the RPCs through the servers to get it done. So we'll show a picture of that. And we don't actually replicate between clusters. There's tools, and we'll mention a few, but in general, every cluster has its own RAF consensus group, its own group of servers, its own KV store, its own service catalog. They're all readable from one another. They're writable, and you can control that with access control lists, but we don't actually replicate the data. So just an important note there. Here's an example of how, like, once you have a federated cluster, in data center 1, I say Consul KV put, data center equals data center 2, hello world. So I wrote across, maybe from Europe to Asia or whatever. And for reading that information out, similar, I can just do a DNS request. I can say, find me consul.service.dc2.consul, and I can do that for DC1. So even your crusty app that you can't compile anymore that can do a DNS lookup can go find stuff from some other data center across the world. So it's exposed in DNS, it's exposed in CLI commands, it's exposed in all the HTTP endpoints. How does this work? Sort of the oldest method is basic federation, which is, if you see it in the Consul documentation, it's always called the WAN. This is available in the open source and Consul Enterprise, and it basically uses the exact same gossip mechanism that we use inside of a LAN. We use sort of another instance of that to federate the servers. So it's another instance of the surf library, basically. It has WAN-oriented timing, so it's not trying to quickly detect nodes failing on a 10 gigabit network. It's trying to deal with something that might be hundreds of milliseconds away. And it's just among the servers. So remember we said the clients actually don't interact with each other when you federate, it's just the servers. So for the WAN functionality, you make a fully connected mesh of all your servers. It's a different port number because it's a different instance. You have to manage the gossip keys the same way, and it'll do RPC forwarding to service those requests. So if you make a query in data center 1 for something in data center 2, your client is going to talk to one of its servers in its local data center because that's all it knows about. The server there on the left is going to forward it on to a server in the other data center. That one might have to send it to the leader depending on what it is. That's all sort of hidden away. And then that answer comes back. So how do you form these types of clusters? There's Consul join -WAN. There's other ways to do this, but this is an example. So you join it to just one other server in the cluster, and it'll join together. And then now I can make queries across either of those data centers from either side. We recently added something that's into Consul Enterprise called network areas. And this was sort of a response to a lot of the enterprise customers we had just sort of weird networks that had constraints. I can't mesh all these. These two can talk to each other, but not these ones. So we created a new model. In terms of how it's exposed to all your endpoints and DNS and all that, it's identical. You have a data center name. What's new about network areas is you basically define a relationship between a pair of clusters, pairwise. They sort of both opt in and then they link up. It uses the same gossip protocol, but in this case, it actually uses just the RPC port. So we transport it all over the same pipe that RPC forwarding works over. So that can be secured with TLS, so you don't have to manage gossip encryption keys. That was the other thing. With sort of massive numbers of federated clusters, it was hard to coordinate the key rotation among your worldwide group of people. So this just uses TLS for everything and eliminates that step. So in terms of what these federations might look like, a really common one is sort of a hub and spoke configuration. So you have one like management cluster. These are clusters, that's why I put the dash lines, even though it sort of looks like nodes from before. So you have like a hub that's like a management thing, and then a lot of people have like customers or whatever that have each cluster, and they don't want the customers to see each other, but they want the management hub to be able to reach down and see into all of them. Or maybe they have their vault up in the hub and they want to discover vault or something like that. So this is a super common pattern. And then the other pattern was just weird stuff. I have these three and this other one, and these can talk to these, but not those. So this has like a sub-hub of DC5, and then 1, 2, and 3 have like a weird triangle, and 4 is like some other thing, PCI thing that can't talk to anything else. So it supports basically any sort of graph relationship you can come up with. So how does that work? You create the area. So in the first data center, that first line, you're basically saying, I'm creating an area with DC2, and then on the other side, you say, I'm creating an area with DC1, and then the third command joins them, and then there's a command to manage your areas. Note this has the round trip time estimate in there, which is kind of cool. That's coming from the network tomography system. This is a more flexible way. In terms of how your applications consume it, though, it's identical. So it's more about making, if you have a few things, you can use the WAN and it works fine. If you have a lot of things and you can mesh, the WAN totally works fine. But when you end up with, many, many things and sort of non-mesh requirements in terms of how your things connect to each other, network areas are a good option for that. So once you've federated clusters, operationally, we do have a built-in tool for ACLs. So there's some interesting stuff built into Consul to help your cluster keep working, even if your ACL data center is out. The ACL data center has to be one of your clusters in Consul. And there's some external tools that we provide. There's a tool called Consul Replicate, so it'll let you pipe portions of your KV store between clusters. But other than that, there's not a built-in replication model, kind of like Vault has. We added something called join flooding. So we use the knowledge that we have within the cluster of where the servers are to make sure all the servers are participating in the federation. That used to be a big hassle, actually. It was easy to forget a server, and it would sort of work, but you'd only have like 2 of your servers working, talking to each other. This just automates that. You don't have to deal with that. And we also added something called soft fail. So if you, one thing that was super common with the WAN is you might have some pair of data centers that can't talk to each other because the line between Europe and Asia is down, but the US can talk to both of them. And that used to cause a lot of, like if there was churn in the sort of gossip layer on the WAN, you might get flapping where you'd pull Europe and Asia out of service from the US's point of view, even though everything was fine there. So with soft fail, we take the gossip information on the WAN and sort of treat it as informational but not authoritative, and we make sure if the connections are still working, we'll keep using them. And then this last part of this, if we've tried all the servers and none of them are actually working, then we declare that data center is offline from a particular data center's perspective. And so it's kind of like a circuit breaker. So you won't get these long-lived, sort of long things waiting to time out. So that actually is a lot more robust as of 0.8 with the soft fail. So that was just a super common thing, is you would pull it out of service without it actually being out of service. So costs, like we said for gossip, it's super small fixed network load, even lower because it's just the servers. For the WAN option, you do need the fully connected mesh. If you're using network areas, it's all just one port and one protocol. For the WAN, you got to manage gossip keys. For network areas, you can just use TLS to secure everything. But massive numbers of clusters, you can federate them. You can do whatever topology you want. And we get the same network topography round trip time measurements. So in my last 3 minutes, we'll go for our last massive category, which is massive power. So we'll talk about how we sort of exploit the scale within our cluster and the ability to federate in sort of an interesting way using a feature called prepared queries. So what these are is it's basically a centrally managed policy that lets you, as a kind of at a cluster level, configure dynamic behavior, and then your apps sort of consume it in the same sort of DNS way. So it's a policy that you can configure centrally, but will be applied across your whole fleet. So you can say, like, look up this service, and if it's not there, go look here. It's kind of it's an interesting sort of centralized look at service discovery. You can access these through the REST APIs or through DNS, and this sort of will unify everything we've seen so far. So here's how we make a prepared query. In this case, it's a template. So I won't talk about the details of this, but it's basically going to match anything, let's say in DNS, it'll match any name.query.consul, and it'll basically plug the name you gave as the service name. And then the interesting bit to this is that we defined this failover clause that says nearest N3. So what that means is look locally, but if you don't have anything locally, just look at the next nearest 3 Consul data centers by round trip time. You didn't have to say look in this order, you just said look at the next nearest 3. So let's see sort of a worked example of how this would come together. So in this picture, there's lots of little dots and stuff, but I'll try and summarize. There's basically 3 Consul clusters here that are federated. There's the one in the sort of left side, and I've sort of blown up a few parts of that. The database is running over there. I have some app that uses the database. The database has a Consul client agent on it. The app does as well. The blue things are the Consul servers over there. So the left side is sort of a data center. On the right, the upper one with boxes still, is another data center somewhere else in the world that also hosts an instance of the database. And then the sort of cluster of dots at the bottom, it's not going to be involved in our example, but that's another place where the database is running. So you can imagine like I've got read replicas off in these different continents. So the first step is the app wants to talk to the database So you can see the DNS arrow coming down from the app to its local console client. It says, where is db.query.console? Console, it has a healthy instance of it. It gives it the IP address. The app connects to it. Let's say that machine just spaces out and dies. So it didn't, we didn't shut the database down, it just died. The cluster, so through LAN gossip, is detecting that, and it's feeding back that the node failed to the console leader server, who pulls it out of the catalog. The app who experienced their connection get reset does another database query for db.query.console. Same thing, they talk to their client. But because we defined that prepared query, it's going to look locally, see that it's not there. It knows that the median round trip time to the upper cluster is 111 milliseconds. The other one is 129, so it's going to pick the next nearest one, send an RPC over there, say, do you have a database that's healthy? It will return the IP of that instance of it, and the app's going to connect to that and keep chugging along. So we basically made a series of single line configuration changes to our app and got to geo failover. So with no service discovery, we have like a hard-coded host name or IP, so we had to go page somebody and everybody's stressed out. For doing local service discovery, we changed the hard-coded host name to db.service.console, which gives us the healthy one from our local cluster. And then basically by changing it to db.query.console and specifying that 6-line policy, we will get automatic geo failover. And if the data center on the upper right drops offline, it'll try the next one. So you don't have to configure any of that as an operator. It's a little quick, but thank you very much.